Hi again. So I want to show you how to put in the data into GeoGebra as well. So I have a screenshot on the notes and I'm going to go over to GeoGebra. So in our statistics tab, remember it starts looking like this with the normal distribution. Click on the statistics tab and at the very bottom we have goodness of fit test. The other one says chi-squared. There's two different chi-squared tests, so the one we want is goodness of fit. And then we need to put in the number of rows, which rows and columns can be switched. So in our table, they were actually columns. So it's really the number of categories we have. We have 5 categories, okay? And this percent column, I think you can use if they're all the same, but ours are going to be different. So I'm going to label them real quick here. And actually, so the tab will just go across. So I'm going to kind of repeat our table here, 384. And our expected, let me find our expected counts. 217.95, tab, black. So notice that in GeoGebra, it doesn't do the expected counts for us, okay? That is one drawback, so I would probably lean towards stat key, but I just want to show you another thing on here. So black 117, 261.54, Hispanic 114, tab 174.36. White 780, 784.62, other 58.14.53. Okay, it does total them, so they both should add up to 1453, which is our total sample size, so that's really good. And then look down at the bottom here. It says goodness of fit test, degrees of freedom. So we have to learn what that means. And then it has our chi-squared statistic. This is the same thing we got, right? 357, 362, or 3. This is slightly different. And then a p-value, okay? So this is telling us the p-value is 0. So we don't quite exactly know how this chi-square distribution works yet, but we do know a small p-value is significant, right? So let's use this to write out our conclusion, and then I'll show you more about the chi-square distribution, okay? So I'm going to go back to the notes, and this is what we had. Statistics tab, goodness of fit test, and we put in all of our stuff, double check the total, and this is our p-value, and the chi-squared is our test statistic. Okay, so let's write our conclusion, and then of course we'll keep talking about this and I'll show you all about the formal stuff, okay? So remember that our null was that it matches this distribution, right? The distribution in the jury pools matches the census demographics. So we know from prior tests that a small p-value means it's significant. That means we reject the null. So that means at least one proportion is different, okay? And we could look at those expected counts and probably see which one or ones are different. So let me write the conclusion right here. With a p-value of 0, we reject the null hypothesis. Right, and I could also write this is less than 0.05. Okay, we got a p-value of 0, so that is very strong evidence. We have very strong evidence that the jury pools in Alameda County do not match the census demographics for race and ethnicity. Okay, and remember, another way to say that is at least one proportion is different. Okay, so there are different ways to word it, but I do really want to make sure we get the context in there. Okay, so I wouldn't just want to say at least one proportion is different. We want to get the jury pools, Alameda County, and demographics, racial demographics not matching. Okay. Okay, great. So that is our conclusion, but we still don't fully know the middle part of this chi-square distribution, right? So let me show you how we can get this p-value using our, well, let's go to the distribution. So as you might imagine, there's a staplet for that. Finding chi-squared probabilities with staplet. Okay, so let me go over there and show you how this works. Now I have the normal one open, and you probably have a direct link to this, but I'm just going to go to staplet.com because that's the fastest for me. And under probability, normal is what we have been using so far, but there are tons of distributions. T distribution, here's the chi-square distribution. Okay. Calculate an area, so a p-value is an area. Now, oh, we need to know degrees of freedom. Well, they said 4, right? GeoGebra told us 4, okay? I'll explain why in just a moment here. Now, this is always a right tail test. So there are options, but because we're talking about the amount of error or difference, 0 is the smallest it could be, and we're always going to the right. Okay, it can't be any more perfect than 0. Then we put in our test statistic right here. So that is the 357.362, and calculate area, and that is where that 0 comes in. Okay, so that kind of shows you how we're getting this p-value, okay? So let me just highlight some instructions on here. So calculate an area, Still got to tell you about the degrees of freedom. And we put in always a right tail test, put in our test statistic, and that's our p value. Okay, so just like you are used to with the normal curve, but with the chi-square distribution. Okay, let's go to the next page. I'll show you a little bit more about this chi-square distribution. Okay, so the chi-square distribution, as you saw, it only has one input. Like normal has two inputs. It has a mean and a standard deviation or standard error, depending on the context. There's only one input, which is degrees of freedom, okay? Now it has to do with how many categories there are, okay? And let's look at different degrees of freedom. So if I go back to this, and I want to match this next graph, so I want to put degrees of freedom 2. Let's see what that looks like. Interesting, huh? So that mode is right at 0. The tallest point is at 0, and it comes down about 10. The next graph I have is 4. So you can kind of just play around with this, and that's the one we had before. What if I make this even bigger to 16? Okay, and then you can see it is really hard to get no error. It's kind of shifted over to the right and a little more symmetric, but still skewed to the right. So you can play with this, try 50. Ooh, so it might approximate a normal distribution. A lot of things do. Okay. Okay, so let's go back to our notes here. And let's highlight a couple things about this. Okay, so for this distribution, the mean is actually at the degrees of freedom. So degrees of freedom 2, this is the mean. And the mode is at degrees of freedom minus 2. So if I go 2 minus 2 is 0, that makes sense. That's where the mode is. Right? And one thing I didn't tell you yet is that it's always one less than the number of categories. Okay, so we could say number of categories minus 1. And that is very consistent for degrees of freedom. So meaning if we knew the numbers for 4 of the categories, we would know automatically what the 5th category was, right? Because that fixes the last one. So the degrees of freedom is always one less than the total. Okay, so for 2, that means we have 3 categories. If we were using degrees of freedom 2, we'd have 3 categories. Okay, and so then as we go to the right, this is more error. Right, 0 would be no error. To the right, we get more error. So if we have a small p-value, that means we have large error. Okay, kind of that's what happened with the jury pool. If we have a large amount of error, we're going to reject the null and say there's a difference, right? That means there's a significant difference. Okay. Let's look at the next graph. So if we have degrees of freedom 4, that means we have 5 categories, and that is the one we were looking at. And you might notice that looks similar to what we originally saw in StatKey with the simulation. Okay, so the mode is 2 less, so that checks out. The peak is at 2, that's the mode. The mean should be at 4. Okay. And then let's just take, let's say we had a smaller one. Let's say we had a test statistic right around here. Always a right tail test. Okay, so let's say we had a larger p-value. Right, so we had a smaller error. That would give us a large p-value, right? This area would be bigger. Then we would fail to reject the null. That would mean we don't have a significant difference. Right? So how much error is too much? That's going to depend on our significance level, right? How small of a p-value is small enough to reject the null. Okay, so this is checking out with the way our hypotheses are set up and the chi-square distribution and this concept of the error getting larger to the right. Okay. Let's look at one more graph. So the 16, that means our mode would be 2 less than that, so 14 would be our mode. 16 would be our mean. And these are getting closer and closer, so you can see it's getting more and more symmetric. Getting close enough, and it does approximate a normal curve if you get your degrees of freedom high enough. So you could try that. So let's make a note about that. As degrees of freedom df increases, the chi-squared distribution gets less skewed and approaches a normal curve. Okay, so just keep seeing that normal distribution. Okay, great. In the next video, we'll go over the actual steps to the test and conditions, so I will see you there.